A function that calls itself sounds like a recipe for an infinite loop, like two mirrors facing each other forever. And yet recursion quietly runs your file folders, your undo button, every JSON parser, and half the algorithms you'll ever meet. So how does it call itself without spiraling into chaos? Recursion is elegant, a little spooky, and a favorite interview test, because it reveals whether you really understand the call stack. In the next few minutes, we'll make that stack visible, and the spookiness will disappear. This is Logic Lab, where computer science becomes something you can see. Today, how a function can call itself over and over and still come back with the right answer. Let's use factorial. 4 factorial means 4 times 3 times 2 times 1. The recursive insight, 4 factorial is just 4 times 3 factorial. The problem contains a smaller copy of itself. So we write it in 2 parts. The recursive case, n factorial equals n times n minus 1 factorial, the function calling a smaller version of itself. And a base case, which we'll get to, that tells it when to stop. Here's the key idea everyone misses. When 4 factorial calls 3 factorial, it doesn't finish, it pauses, frozen, waiting for the answer. That paused call gets stacked on top of a pile the computer keeps, the call stack. 3 factorial then calls 2 factorial and pauses 2. 2 calls 1. Watch the stack grow, 4 waiting on 3, waiting on 2, waiting on 1. Each frame remembers exactly where to come back to. Now the hero, the base case. 1 factorial is simply 1, no more calls. This is the stop sign that ends the descent. The moment we hit it, the stack stops growing and we finally have a real answer to return. And if you forget the base case, the function keeps calling smaller and smaller forever, the stack grows without limit, and the program dies with the famous stack overflow. Every recursion needs a base case, that's the rule. Now we unwind. 1 factorial returns 1. 2 factorial, which was waiting, multiplies 2 by that 1 and returns 2. 3 factorial wakes up, multiplies 3 by 2, returns 6. 4 factorial, the very first call, finally gets its answer. 4 times 6 is 24. The result bubbled all the way back up the stack. The pile empties in the exact reverse order it was built. Recursion shines whenever a problem contains smaller copies of itself. Walking a folder tree, exploring a graph, the divide and conquer sorts from last time. Anything branching or nested is often clumsy with loops, but beautiful with recursion. Anything recursive can be rewritten as a loop, and a loop won't fill the stack. But for self-similar problems, recursion is dramatically clearer. You just describe the problem in terms of itself, plus a base case, and the call stack does the bookkeeping for you. Recap. A recursive function solves a smaller copy of itself, then combines. Each call pauses and stacks up on the call stack. The base case stops the descent, forget it, and you overflow. Then the stack unwinds, answers returning in reverse until the original call gets its result. Now you can see the stack behind the magic. Recursion isn't chaos, it's a tidy pile. Next, we point this superpower at networks. How do you explore a maze, a map, or a social graph? 2 ways to explore anything next on Logic Lab. See you there.